Friends, today we will discuss about the steam concept series video 2. So look into these pics. Lots of things are depicted about the steam concept. You will come to know later what are the significance of these figures. So the steam concept series for process design engineering will cover the what is the steam, which we already covered, and the second lecture we are covering the concept of critical point and the concept of triple point and concept of a specific heat capacity. In the third lecture we'll cover the steam phase diagram. We'll try to cover this in a lecture in this lecture too, the steam of phase diagram, but if it remains then we'll cover in the third video. And in third video we'll cover the enthalpy of water or sensible heat of water, enthalpy of evaporation or latent heat of water, enthalpy of dry saturated steam or total heat content of dry saturated steam, and steam dryness fraction. In the next lecture we will cover the practical use of entropy and practical use of enthalpy as isoenthalpic process and steam calculation, and isoentropic process and steam calculation. In the further lecture we'll cover the understanding of steam tables, how flash steam generated, and some conceptual example, and steam jet ejector and thermal compressor design calculation. So following concept to be discussed in this video: critical point, triple point, specific heat capacity. So this is about me. I am Lokesh Singh, CUMD Petrohorizon Oil and Gas Engineering Private Limited, and this is my education qualification and experience in brief. And you can visit our company website www.petrohorizon.com, and you can also visit our Facebook page Petrohorizon Oil and Gas Engineering Private Limited to know about more video, our offerings, our hirings, and our courses. So come to the point. What is critical point actually? The point at which the saturated lines, liquid lines and saturated vapor lines meet is known as critical point. You can see in this phase diagram. So this is the saturated liquid line and this is the saturated vapor line. These two lines meet at critical point. So this is called at critical point. Now, as the pressure increases toward the critical point, the enthalpy of evaporation decreases as indicated by the decreasing length of BC toward the critical point. You see in this figure, actually this region is two-phase region. So this is the liquid phase region and this is the superheated region. So from this to this point, it means BC length, this indicates the enthalpy of evaporation or latent heat of vaporization. If the pressure is increasing, see the length from here to here is decreasing towards the critical point. That means enthalpy of evaporation is decreasing at the higher pressure. So at critical point, enthalpy of evaporation becomes 0. See, when the if we go here and we measure length from here to here and then further go up and further go up, here the length almost become negligible. That means the required latent heat of vaporization at critical point is negligible. So at critical point, enthalpy of evaporation becomes 0. It means water changes directly into saturated steam at critical point if heated slightly. So this is the reason that we assume minimum value of latent heat of vaporization 50 BTU per hour for sizing calculation of safety valves where set pressure of vessel is more than the critical pressure of fluids in the vessel, because as per the phase diagram, latent heat of vaporization HFG as denoted in the steam table at critical point become almost 0. Therefore in supercritical region very less latent heat is required for the evaporation. This concept you will come to know when you will learn how to size the critical PSV, pressure safety valve, or supercritical PSV sizing. This is for those who are working in process design field and having 2 to 3 year experience. They can understand this concept if they have done this critical PSV sizing or supercritical PSV sizing. If a fluid is under critical temperature and pressure, if it is further heated or pressurized, then it becomes supercritical fluid. See here in this phase, up to this point, and this corresponding temperature and this corresponding pressure, this is critical temperature and critical pressure point. If the we heat further and temperature go beyond this point, so and the pressure goes beyond this point, so we call this fluid is a supercritical fluid. So now, if liquid at supercritical condition will directly change into saturated vapor without using latent heat of vaporization, because there is no requirement of latent heat of vaporization as stated. The critical point occur at 374.15 degrees centigrade and 221.2 bar absolute for steam. Above this pressure, steam is termed as supercritical steam. So this is critical point on phase diagram. So you can see this is a phase diagram, temperature versus enthalpy, and here you can see at point A the water is as a cold liquid, and if we heat water, so temperature start increasing. So at point B the water started boiling, so corresponding to point B the enthalpy, this one, see HF, this is a sensible heat of water. That means here, or you can say this is the heat of saturation or enthalpy of saturation. So at point B the water is at its boiling point and it is saturated with heat. So if we heat further this water, so what happens, water start boiling and the steam start producing, but the temperature of water remain constant and the steam produced, which is saturated steam, the temperature of steam also remain constant. Means if at 1 atmospheric pressure the temperature of saturated water is 100 degrees centigrade, so the steam produced will be at 100 degrees centigrade at 1 bar. So if we further keep on heating the water, the steam is getting produced more and more, but what is happening, the specific volume of the steam is increasing. That means the density of steam is decreasing. So what is another thing is happening, the dryness fraction of the steam is also increasing. At this point the dryness fraction is 0, and at this point, at point C, the dryness fraction of steam is 1. So here the steam is called dry saturated steam. So if we increase the pressure, so let's say these are the constant pressure lines, these are constant pressure lines, so this is also a constant pressure line. So let's say this is at atmospheric pressure and this is at higher pressure than atmospheric pressure line. So you can see the length from here to here is less than length BC. That means this BC length indicate HFG, the latent heat of vaporization or the enthalpy of vaporization. So this length here at higher pressure is less. That means at higher pressure the latent heat of vaporization decreases, and that's why it's very economical to produce the high pressure steam as compared to low pressure steam, because the latent heat of vaporization at higher pressure is less, and if we go further up the latent heat of vaporization is decreasing because the length is also decreasing. At critical point the latent heat of vaporization almost reduced to negligible. So this, in this phase diagram you can understand that this is the liquid phase region, or we call compressed liquid phase region, and this is the supercritical phase region, and this is two phase region. So there are some points of the critical points, you should know these points. So above critical point only gas may exist. See, this is the critical point. If above this point only the gas will exist, this is the highest point where the liquid can exist. Beyond this point the liquid cannot exist. Critical temperature is the highest temperature at which liquid can exist, as I told you. Any compressor at constant temperature of the critical point will not produce phase change. See, if we are beyond this point, our temperature is beyond this point, so if we compress any amount of, if we do any amount of compression, so the gas phase will not be compressed to liquid phase or the or two phase, or it will not change the phase. So during this vaporization process, see what is happening here. From here to here it is vaporization. So what is happening, both the temperature and pressure is constant. See, as I told you, it's at, let's say it is at atmospheric pressure and boiling point is 100 degrees centigrade. So this temperature will not change if the pressure is remain constant, and then steam will be produced at 1 bar and 100 degrees centigrade steam up to the point of C. Beyond the point C, if we further keep on heating, the steam becomes superheated and the temperature of the steam start rising beyond the saturation temperature of water at 1 bar degree centigrade. And the difference between the superheated steam temperature and the saturation temperature of water, which is 100 degree centigrade, is called degree of superheat. So at higher pressure, specific volume, which is the inverse of density of saturated liquid, is larger, and the specific volume of the saturated vapor is smaller than the corresponding value at 1 atmospheric pressure. That means here this is 1 atmosphere and this is a higher pressure. So here the specific volume of water is higher and the specific volume of saturated steam is lower as compared to this reference pressure, which is 1 bar. As the pressure increases further, the saturation line continue to shrink. See here, if the pressure is increasing, the saturation line is shrinking, means it's getting shorter, and it becomes a point when the pressure reaches 221.19 bar for the case of water. This point is called the critical point, and it is defined at the point at which the saturation liquid and saturated vapor states are identical. Here, see, the saturation liquid line and the saturated vapor line is meeting here. So this is the point where the saturated liquid and the saturated vapor are identical. The phase cannot be separated, defined. So the temperature and pressure and specific volume of substance at a critical point are called respectively critical temperature and critical pressure and critical specific volume at this point. So let's say example, if a closed vessel filled with a gas is heated to critical temperature, then this gas cannot be liquefied by any compression till the temperature of this gas is at critical temperature or above. Means if the gas temperature filled in the vessel is at critical temperature or above this temperature, then if we compress it at any amount, then it cannot be liquefied. It cannot be bring down to this region or this region. So only way to liquefy such a gas is to reduce its temperature first below the critical point temperature. So this is the specialty of critical point. Now, at pressure of the critical pressure, there is not a distinct phase change from as seen figure. This is the specific volume of substance continuously increase, means density is decreasing, means the and all time there is only one phase presents. Eventually it resembles a vapor, but we can never tell when the phase change has occurred. See, beyond this point, see, up to this point you can see there is two phase region, but beyond this point you cannot define when the phase change occur, but the only phase is here is vapor phase. Above the critical state there is no line that separates the compressed liquid region. As I told you, this is compressed liquid region and this is superheated gas region. However, it is customary to refer to the substance as superheated vapor at temperature of the critical temperature and a compressed liquid at a temperature below the critical temperature. The saturated liquid states in figure can be connected by a line called saturated liquid line, and saturated vapor states in the same figure can be connected by another called the saturated vapor line. As I told you, this is saturated liquid line and this is saturated vapor line. So these lines can be connected by these 2 points. These two lines meet at the point critical point, forming a dome. So these two lines is meeting here, forming a dome shape. This is a dome shape, and here this is a critical point. Now all the compressed liquid states are located in this region. To the left of the saturated liquid line are compressed liquid region. As I told you, this is compressed, the left side of this liquid saturated line is compressed liquid region, and All the superheated vapor states are located to the right of saturated vapor line are called superheated vapor region. So from this is a saturated vapor line. So all the fluids here is superheated vapor region. This is superheated vapor region. So in these two regions, the substance exists in a single phase or a liquid or a vapor. All the states that involve both phase and equilibrium are located under the dome called the super saturated liquid vapor mixture region or wet region. This is called saturated liquid vapor region or a wet region. Here the dryness fraction is not equal to 1. At this point the dryness fraction is 1. So this is dry. Actually here we call the saturated steam as a dry saturated steam. Here between this region the steam produces wet steam. So now this is triple point concept. So the point at which the sublimation line and vaporization line and the melting line meets on a phase diagram is known as triple points. So this is PT curve. So here you can see this is sublimation line, this is vaporization line, this is melting line. These two lines are meeting at triple point. This is called a triple point. So this is the highest point where the solid, liquid and vapor can exist in equilibrium, whereas if we further increase the temperature and pressure, so the point reached here is critical point. This is the highest point where the two phase liquid and vapor phase can exist in equilibrium. This is the difference in triple point and critical point. All the three phase solid, liquid, vapor of any substance can only coexist in equilibrium at a certain temperature and pressure. This point is known as triple point in phase diagram. So which is this point. So here the solid, vapor and liquid can exist in equilibrium. And the corresponding temperature, if you see corresponding pressure and corresponding temperature, this is called triple point pressure and triple point temperature. So triple point temperature of water is 273.16 Kelvin and the pressure 0.00611 bar is a triple point pressure. This pressure is very close to absolute vacuum or perfect vacuum. If the pressure is reduced further at triple point, if we reduce the pressure here, so what is happening actually? Temperature also reducing, so it goes, this pressure is very see, if the pressure is reduced further at a triple point temperature, then ice instead of melting sublimates directly into vapor. So in this region, so if we decrease the pressure, the temperature also decrease. So what is happening? The ice is not melting, it directly converting into the vapor actually. It can be observed from the water phase diagram that triple point is equilibrium existence of three phase, whereas critical point is equilibrium existence of two phase. This is the difference between triple point and critical point. So now this is very confused concept of specific heat capacity among the engineers, because sometimes they have to guess by seeing the liquid that what could be the specific heat capacity of this liquid, or whether this liquid heat capacity value is correct or not. By knowing this concept, you will be able to identify what could be the possible specific heat capacity of liquid. See, let me explain you the practical definition of this specific heat capacity. It is the amount of heat required to rise temperature of 1 kg substance from 0 degrees centigrade to its boiling point at atmospheric pressure. So at atmospheric pressure, which is 0 bar gauge or 1 bar absolute, water boils at 100 degrees centigrade and 419 kilojoule of energy is required to heat 1 kg of water from 0 degrees centigrade to its boiling point 100 degrees centigrade. So the specific heat capacity value of water, which is 4.19 kilojoule per kg per degree centigrade, is derived from this definition. If we divide 419 kilojoule by the temperature difference between 0 degree centigrade and 100 degree centigrade and 1 kg, as it is specific, so it's per kg, so the value comes 4.19 kilojoule per kg per degree centigrade. In this way, by knowing the boiling point of any substances at atmospheric pressure, you will be able to guess the value of specific heat capacity of that substance by comparing its boiling point with water. Let's say the boiling point of petrol is 60 degrees centigrade and we want to know the specific heat capacity of petrol. So boiling point of petrol at atmospheric pressure, which is 60 degrees centigrade, is around half the boiling point of water. Therefore, the amount of heat required to rise the temperature of 1 kg of petrol from 0 degrees centigrade to 60 degrees centigrade is approximately half as compared to water. Therefore, the specific heat capacity of petrol will be around half of the specific heat capacity of water. So it will be around 2.1 kilojoule per kg per degree centigrade. So I think now you can guess the specific heat capacity of any liquid substance if you know the boiling point of that substance or liquid. So this is Petro Horizon offering for petroleum and chemical engineering students. We offer 1 month value-added training courses which is of 60 hours and training fees is 7,000. And the second course is 6-month engineering design skill development training and placement assistance program. Here we provide 300 hours rigorous design training, and we provide also a certification. Training fees is 50,000, could be paid in 2 installment. So we also provide the assistance in completing the design projects for third and final year chemical, petroleum, mechanical engineering students. So note the project time and the cost depends on the student choice of design project, but it's very nominal, it's not very high. So we provide 3-day demo classes, training classes and awareness classes at Dehradun Training Center before taking decision to join our training program, because the student could be thinking that whether I should join or not. So they can join our 3-day demo training classes by registering with us, and then they can think about whether this course is worth for them and they want to continue or they want to join our course or not. So registration is open from 5th of May 2017. You can contact us with this email ID mentioned here and the phone numbers. So please subscribe to our YouTube channel to get updated with new videos. It will encourage us to upload more videos for your knowledge and design concept. We will be keep uploading the complete series, and after that we will start putting next series which will be very conceptual for design intent. So thanks a lot for watching our video. Please subscribe our YouTube channel and like us. Thanks a lot. Bye bye.